Here we will look at a facility in the software you can use if none of the cross-sections, standard cross-sections which are available in the software, if they don't seem to fit your data. We'll take an example of silicon dioxide. So here we have silicon dioxide, pure silicon dioxide, and we have some oxygen islands grown on a substrate of silicon. We just look at the pure silicon dioxide spectrum. That's the oxygen 1s from silicon dioxide. It's here, and we have an energy of 970. And if you look up in the IMFP calculator, you will end up with an IMFP of about 28. So we have 28 here in the IMFP, and we can analyze the data. We know this is pure silicon dioxide, so we just put in a thick layer. So it goes from 0 to infinite thickness. We know this is true because it's pure silicon dioxide. Now with the universal cross-section, the fit is good out here, but the fit is not so good in this region here. And that's because in silicon dioxide we have a fairly sharp plasmon structure here. So to model that, you could use the available silicon dioxide cross-section, which is determined from reflection electron energy loss spectroscopy. But suppose you didn't have that, and you would like to analyze such a spectrum, and you didn't have an available cross-section. You can use this facility here with an external cross-section. A new window opens up, and here you can create a cross-section. You can do that in two ways. Either you can create a new universal cross-section. You can make a blend of cross-section. In the next example, we will look at this facility with the blending of cross-section. Here we'll just look at the facility to create a new universal cross-section. You can do that with a 2-parameter cross-section. The parameters are here, B and C, and you can change this. Or we can use a 3-parameter cross-section. In this case, we have a fairly sharp plasmon, so we use the 3-parameter cross-section. You can vary the C parameter, and by varying that, you vary the position of the plasmon. At the same time, you would move the analysis over here. You see that? So we change it here, both of these move. So we start by putting this more or less over the structure we see here in the spectrum. We can also vary the width of that. We do that by the parameter D. So we increase that, the width of that increases. So we can maybe move that up to a couple of hundred here. And now the width is more or less correct. We can move the position a little bit further in. So we have a good account for the structure here. We get a smooth background corrected spectrum in this range. You can also save this cross-section by clicking here, and then you can put in a file name and you can save it up here, and you can use it later on as a cross-section for your analysis. You can also have used here the default silicon dioxide cross-section. If you use that, you see we get about the same, a little less correct position of the silicon dioxide plasmon peak here compared to the external cross-section. So actually this external cross-section would probably be slightly more accurate to use than the default silicon dioxide cross-section. If you use this in practice, I've done that for the silicon dioxide islands form on silicon, you get about the same result to within a few percent. So it's not that critical how you do it. But this shows how you can find a reasonable cross-section for cases, for samples where you don't have a cross-section available. Usually you would not need to use this because the cross-sections you have here are usually sufficient. But it's nice to have in some cases.